Grade 12, hope you're doing very well. So today we're talking about the graph of a cubic function, and for me it's very important to explain the concepts very well before we do an example. Okay, so in order to do that, I'm first going to draw a typical cubic function, and then from there on we'll do the actual example. Okay, so here's your typical cubic function. So let's take it step by step. Right over here, you have your y-intercept. Now, how do you normally get the y-intercept? You make x equal to 0, and then you'll get that coordinate. It stays the same for cubic function. Okay. Right over here, you have your x-intercepts. And how do we get our x-intercepts? By making y 0. But now you have 0 equals, and then you have a cubic expression, right? So we are going to use the factor theorem to get the first factor. And then from there on, we're going to use long division or synthetic division to get the other two factors, or the other expressions, so that we can actually get all three of the x-intercepts. So that's the strategy. Now the next part of the strategy is to get the two turning points. So here you have one turning point, there's the other turning point. They are also called stationary points. Okay, so in a test, if they ask you for stationary points, they are talking about the turning point. Okay, and you know that at the turning point, the gradient will be 0. Can you see it? Both, it would be horizontal lines, tangent, so that means the gradient will be 0. Okay. So our strategy is to get the derivative, the first derivative, and make it equal to 0. And then we'll get our x coordinates. And then we will substitute our x coordinates into the original expression of the function. And that will give us the y coordinates of our turning points. Okay, now in the book they put the next part I'm going to talk about only later, but for me it's very important that we practice from the start the way that you will apply this in a test. Okay, and this is something called concavity. Okay, it has nothing to do with your teeth or anything like that. Concavity basically refers to how the graph is expressed. Like you will see, this one is how we would refer to as a frowny face, right? And we would say this is concave downwards. Okay, and this part of the graph is concave upwards. Let me quickly draw a parabola. This one is concave downwards. This one is concave upwards because of its shape. Okay, so that's what we're talking about. Now, a concave downwards graph is also called negatively concave. A positive graph is positively concave, so keep that in mind. Okay? So somewhere with a cubic function, this changes. You can see all of this is still concave negatively or downwards until a point somewhere around about here where it will change. Now the graph is concave upwards. Now this point, we call that point the point of inflection, and that is what we need to calculate as well. Okay, so the gradient is a rate of change, right? So this is our graph. Here we go. Now how the graph's gradient changes, or how the graph changes, is the gradient, right? There's a strongly positive gradient all the way till here it becomes 0, and then it will become negative and become more negative until a point where it will become less negative again, and that point where it changes is the point of inflection. Then it will become 0 again, then it will become more positive all the way to there. So the gradient shows you how the graph changes, but how the gradient changes, that would be determined by something called the second derivative. Okay, so the first derivative shows you how the graph changes, So now the second derivative shows you how the first derivative, the gradient, changes. So, and where that is equal to 0, that will be the point of inflection. Okay. Think of it in terms of distance, and the velocity is how, like, kilometers per hour. Like I say, it's a rate of change. Acceleration, or like I say, speed is meters per second, right? But acceleration is meters per second square, right? So that is how the velocity changes. So the velocity is how the distance changes, but the acceleration is how the velocity changes. So that's basically the same principle. And we are going to work with the second derivative to calculate that. And where that is equal to 0, you will get the point of inflection. You will see for any x value left of the point of inflection, if you substitute that into the second derivative, you'll get a negative. And that shows you it's negatively concave. Any x value to the right of this point of inflection, you substitute it into the second derivative and you'll get a positive value because it's positively concave. Okay, and these two, as mentioned, is called stationary points, and this is also called a local maximum, and this is called the local minimum. Okay, keep that in mind. Now we're going to do number 4, exercise 11, as an example. Okay, so here's the expression. Remember our strategy. First things first, y-intercept. Okay, so to get the y-intercept, we're going to make x 0. So then you say k with x being 0 is negative 13. Therefore, it is 0 and negative 13. So this was now to get the y-intercept. Now the second part would get to the x-intercept, right? And we're making y 0 in order to do that. So 0 was 2x cubed plus 3x squared minus 12x minus 13. So now we have our 0 on that side. We can use the zero product rule. But remember, we're starting off with the factors theorem in order to get this, right? So you start with 0. You test for x equals to 0. You can see it won't work because of the negative 13. Then you try 1. You'll see 1. It's very easy. Just say 2 plus 3 minus 12 minus 13. You can see it does not add up to 0. It becomes something like negative 20. So then the next one is negative 1. Let's test negative 1. So, and I've got a feeling this will work out. So now we say let x be equal to negative 1. So 2 times negative 1 cubed plus 3 times negative 1 squared minus 12 times negative 1 minus 13. And you will see this becomes a negative, so it's negative 2. This becomes a positive, so it's plus 3. This becomes a positive. Negative 13 remains negative 13, and this adds up to 0. Therefore, x plus 1 is a... Okay, now we're using synthetic division or long division to get the other two. I've written it down. Remember, our expression was 2x cubed plus 3x squared minus 12x minus 13. Put the 0 there, and x equals negative 1 is a factor. So then we can work it out from here. So 2 plus 0 is 2. Negative 1 times 2 is negative 2. 3 plus a negative 2 is 1. Negative 1 times 1 is negative 1. Negative 12 plus negative 1 is negative 13. Negative 1 times negative 13 is positive 13. Negative 13 plus 13 is 0. So remember, this is our remainder. It's 0, it's a factor, it's perfect. So now we know what? We know that it's x plus 1. The expression is actually equal to x plus 1 times 2x squared plus x minus 13. Now we still need to get this into factors, right? And you can clearly see here that we won't be able to do that by just factorizing, right? So we are going to have to use the quadratic formula. So x equals minus b plus minus square root b squared minus 4ac over 2a. So minus b is minus 1 plus minus square root of b squared, which is 1 squared, minus 4 times a, which is a 2, and c, which is negative 13. Remember that, please. The negative, remember the negative, and a is 2. And if you do this calculation, you'll see that x is minus 2,8, or x is equal to 2,3. So here we have our 3 x-intercepts. There we go. So we've got our y-intercepts and our x-intercepts. And now we are going to move on to the turning point. So our initial expression was equal to, let me just get it again, was equal to 2x to the power of 3 plus 3x to the power of 2 minus 12x minus 13. And now we are going to get the first derivative. It's equal to 6x squared plus 6x minus 12. And we want this to be equal to 0 for the turning point, right? So this is for the turning point. I'm just going to say TP here, you know what we're doing. Okay. Then I can divide with 6. So 0 equals x squared plus x minus 2. And if we factorize, let me just write the top. You will see it becomes x plus 2, x minus 1. Therefore, x equals negative 2, or x equals 1. So these are the x coordinates for the turning points. So now we substitute this into our original equation. Okay, not the derivative, because if you're going to substitute into the derivative, you're just going to get 0, because these are factors of derivative equal to 0. So now into the original equation, and then you get values of 7 and negative 20. Therefore, these are the coordinates of our turning point. So we have the turning points, we've got the x-intercept, the y-intercept. Now we have to get the point of inflection. Okay, so let me just write down the function again so you can see how it looked like. And then the first derivative was this. And now for the second derivative, it will become 12x plus 6. And remember, where the second derivative is equal to 0, that's the inflection point. Okay? So 0 equals 12x plus 6. So negative 6 equals 12x. So x equals negative a half. Now to get the coordinate of the actual point of inflection, you have to substitute the negative a half into your original equation, the function. Remember, we're drawing the function, we're not drawing the derivative for the second derivative. And then you get negative 6.5. So now we are set to draw this graph. So if we draw the graph, it will look something like this. Okay, so let's have a look. You have your x-intercepts, negative 2.8, negative 1 and 2.3. You've got your y-intercept as negative 13. You've got your turning points as negative 2 and 7. And 1 and negative 20, and your point of inflection negative half and 6.5. And again, if you can look at the coordinates of the turning points to determine if it's concave downwards or concave upwards, or you can take the second derivative, substitute in negative 2, for example, any x value left of the point of inflection, and that will give you a negative answer, and you know it looks like that. To the right will give you a positive answer. And that's how you draw a cubic function.